So Vk represents the number of data falling within a particular class interval. So a key feature of a histogram is that we use the area to describe the amount of the data falling in that class interval. We focus on the area, not the height. We use the area. So if we construct a density histogram, then the area of each rectangle will be equal to the proportion of the data falling in that class interval. So that the total area of all the rectangles added together will become 100%. And therefore, to construct a histogram, we need to draw a rectangular block over each of the class intervals with the area equal to the proportion, which is equal to the frequency divided by the sample size. Now, we need to determine the height of the rectangle if we want to draw the rectangle. So we know that for a rectangle, the area is equal to the width multiplied to the height. And therefore, the height of the rectangle will be equal to the area divided by the width. So that's why we have this formula. The height of the rectangle above on each of the class interval is equal to the frequency divided by the sample size multiplied to the width of the class interval. That's why we have this formula. Okay? So you should always keep in mind that in a density histogram, the vertical scale here is not the frequency. It is also not the proportion. It is the proportion of data per unit interval. It is given by this formula. Okay? So if we treat this histogram as a probability density function, then for any x within a particular class, the histogram value of this x is equal to the height of this block, equal to Vk divided by n times h. Okay. So this is the feature of the histogram. Now based on this, maybe you can try to work on question number 3. You are given a frequency table, and if we construct a histogram based on this table, what will be the height of the density at x equal to 20 and at x equal to 80? So just based on this formula, try to compute this density value for part A and also for part B. Okay?
I'm trying to, yeah. Oh, that was from a while ago.
Yeah. Yeah. Working on research number 3.
This column is VK. Okay? Frequency. VK stands for the frequency. If you complete part A, you may proceed to part B. N is the sample size. H is the width, which is N. Because we have trained and standardized it into total area equal to 1, so we need to divide everything by total. So the whole area will be equal. That's why it's completely density. Okay, maybe I just briefly walk you through the solution. Now, I would like to explain it again. In a density histogram, the height of each rectangular block is determined according to this formula, or this form, this is here, which is equal to Vk divided by n times h. Now, what is Vk? Vk is the frequency of the data falling within this class. N is the total number of data, which is the sample size. H is the width of the class. So in this problem, if we want to determine histogram at s equal to 20, first of all, we need to locate the class that contains 20. And the class containing 20 is this one, from 15 to 25. So the corresponding Vk is 142. and n is equal to 500. And h is the width of the class, which is from 15 to 25. The width is equal to 10. So we substitute everything into this formula. We get the answer, which is 0.0284. So similarly, the histogram at 80, we need to locate the class containing 80, which is equal to from 75 to 85. So the count, the frequency is 0 to 6. The Vk is 0 to 6. Similarly, we divide by n times h. So this is the answer for part A. Understand? Now, next we move on to part B. Part B is corresponding to what will happen if we redefine the intervals. Instead of using the interval from 5 to 15, we start from the interval from 5 to 25. We use a larger interval. So we group, just imagine that we can group these intervals together. We group these two intervals. So we group these two intervals together. Group these two intervals together. Group these two intervals, and so on. And after we group the intervals, just imagine that this time if you want to locate the interval containing 20, to do the calculation again, what will be the Vk? Now this time, since we grouped this interval to this interval, originally 20 is inside this interval, but after we group them together, then 20 will belong to this grouped interval. So the Vk this time will become 83 add to 142. And we divide by n times h. But this time, since the interval has been grouped, so the width of the interval becomes larger. Instead of 10, it becomes 20. So this will be the result of the height of the rectangular block after we group the interval. Similarly, histogram 80 is equal to, this time we locate the interval containing 80. 80, originally it is in this interval, but after we group them, it belongs to this larger interval, which is with the frequency equal to 13 add to 6. So this will be the answer. So just imagine that you have created histogram. One of you try to create a histogram according to A. Another one of you try to create a histogram according to B. Actually, the shape of the graph will not differ by too much, because the value of this and this value of this and this, they don't differ by too much. So one key feature of the histogram is that you can try to redefine the class interval, and it will still preserve the shape of the graph. Okay? So this is also the reason why in a histogram we use the area. We use the area instead of the height to represent the proportion. So that even you use a different definition of the class interval, the shape of the data distribution will be still preserved. Is there any question? Yes?
So what if the new width is 15 instead of 20?
Instead of 20, you can change. Even you use a different class width for different classes. It will still work. Yeah, you can try. You can just try by yourself. Any question? Now, besides the histogram, I would also like you to understand how we compute the quantile. So let's move on to question number 5. About the calculation of the 5-number summary, essentially you need to compute the quantile. Now this is how we compute the P quantile. Okay? To compute the P quantile is a cutoff in the data set. It provides you a cutoff, and you know that about P of the data fall below this cutoff. That's the idea of the P quantile. So suppose I tell you that the scores, the 80 the point H quantile of all the scores of a test is equal to 75. And if you score higher than 75, then you know that you are in the top 20%. So this is how we make use of the quantile. So how to compute the P quantile? Now notice that there are a lot of different formula. There's no common consensus. According to what was taught in this course, the quantile is computed according to this formula. We need to first compute an index. R equal to the sample size F1 multiplied to the P. Then you take the integer part of R, because this R can be an integer or not an integer. So if it is not an integer, we need to take the integer part of R. So we locate the data in the sorted data set with the rank equal to the integer part of R. And then we add to the fraction, there's no plus sign here. It is a product, okay? We need to multiply this add to a fraction, the fractional part of the index, multiply to the difference between the rth number to the next number. The reason is that suppose you determine the quantile located at 4.5 somewhere, the index is 4.5, then you will know that the quantile should be somewhere between the fourth number and the fifth number. And we do the interpolation according to this formula. Okay? This is how we compute the quantile. So according to this, try to work on this question, to compute the 5-number summary and construct the box plot. On 75 quantile. These 5 numbers are the 5-number summary. This is how times order how times so in the sort. Suppose you have the data sorted. More than the largest then how times is the number and rank. So if our time is equal to 1, that is the first one, or if our time is equal to the second. If our time is 2, then that will satisfy quite close to each other.
data set. And for small data set, usually it's not very important to determine if you only have small data set. You know, the quantity is a sample statistic. If you have the data set, you cannot completely tell the others. Every number is a large. So you summarize it by certain point. That's the situation we need. It doesn't matter which way you use. Yeah, this is one way to make judgment. There's no judgment whether it is now this is of course not a statistic. Because if you are to comment on the data whether it is almost accurate, then it is data or you can also compute this yeah, if they're nearly the same thing.
So it's hard to
But then no peer cut off. There's no peer cut off. Which number yeah. They will always
So I guess some of you had got it right. Now maybe I will just say a few words about this. Now, as I mentioned before, the quantile is computed using this formula. And for a 5-number summary, it contains 5 numbers, summarize the data, including the minimum, the 0.25 quantile. We also call this the lower quartile. The median, the 0.75 quantile. We also call it the upper quartile. And finally, the maximum. So in the data set, we do it step by step. For the minimum, of course, it is the smallest number in the data set, and the data set has all been sorted for you. So it is very comprehensive. We got the first number, the first smallest number, 31. Now for the 0.25 quantile, we need to first find the index. So we add 1 to the sample size and then multiply to the p, which is 0.25. The index is 4.75. In other words, the 0.25 quantile is located at a number which is ranked 4.75. So it is somewhere between the 4th number and the 5th number. So the Q of 0.25 is equal to S4. 4 is the integer part of the index. Add to the fractional part, 0.75, multiply to the difference between the 4th numbers and the 5th number. Okay? This is how we do the so-called interpolation. So from the data set, the 4th number is 69 in the sorted data set, 69, and the 5th one is the 70. So we have 69 here and 70 here. So this is how we compute the 0.25 quantile in this. Now, some students ask me if you use a calculator with the quantile function, you may not get the same result. Or if you use R, you may also not getting the same result. This is what I've mentioned before. There are different formula for computing the index, so that the quantile computed will be a little bit different. Okay. Now for the median. Now it depends on whether the n, the sample size, is odd number or even number. If n is odd, the median is located right at the middle, the number at the middle of the whole data set. When n is even, the median will be the average of the 2 numbers located at the middle of the sorted data set. And since n is even here, so that the median will be the average of these 2 numbers. 77, and 79. Now for the upper quartile or the 0.75 quantile, I'm not going to repeat the calculation here. You may do the similar calculation. You will find that it is equal to 87 point something. And the maximum is the largest number equal to 94. Now I would like to say a few words about the meaning of these 5 numbers. So after we computed these 5 numbers, we can report these 5 numbers to the other people. So the 5 number summary is 31, 69.75, 78, 87.25, and 94. So if you want to describe your data to the others without telling them the details numbers of each piece of data, you can report them this summary. For those who received your report, what can they obtain? They can have some impression about the data distribution of your data set. We know that this is the smallest number, and this is the number located at the 25 quantile. So in other words, there will be about 1/4 of data falling within this range. So we have 25% of the data falling within this range. And this is the median. So we have half of the data fall below this. So in other words, we have another 25% within this. So why are we so interested in this 5 number, and we call them a 5 number summary? The reason is that they partition the data set into 4 equal pieces. In each of this region, we have 25%, about 25% of the data allocated into it. So that we just based on these 5 numbers, we have some impression about the data distribution. Now, of course, these are numbers. Human eyes are more sensitive to graphical display. So we may want to turn this into visualization. And graphical display for the 5 number summary is the box plot. Now, before we construct the box plot, we need to first determine the outlier. Now, how can we determine the outlier? Outliers are numbers that are very different from the majority. They are numbers too far away from the majority. So we need some cut-off, some threshold, so that we know that if we have some observation in the data fall beyond this threshold, we will treat them as outlier. So how can we determine this threshold? Now there's a ad hoc procedure. First, we compute the interquartile range. So this is the interquartile range. So the interquartile range is the difference between the 0.75 quantile and the 0.25 quantile. The difference between the upper quartile and the lower quartile. It tells us the range of the data falling within this 50%. We have 25% here, 25% here, so that we have the middle 50% within this range. And in this data set, it is equal to 87.25 minus 69.75 equal to 17.5. This is the interquartile range. Then based on the interquartile range, we extend 1.5 interquartile range from the lower quartile. And we also extend 1.5 interquartile range above the upper quartile to compute these thresholds. So the idea here is that we have the lower quartile, which is already at the lower part of the data set. And we extend this even farther with 1.5 interquartile range below it. So that is already very far from the majority. And if you have a number even below it, then that will be a suspect outlier. Similarly, the upper fence or the upper threshold here, this is the upper quartile. This is 1.5 interquartile range above the upper quartile. So it is already very far from the majority of the data. And if you have observed a number which is above this, of course, that will be also an outlier. So any number beyond these two quantities will be treated as outlier. And in this data set, we have two numbers. These two numbers are smaller than 43.5. And therefore, these are the outliers. Okay? And in constructing a histogram, we will particularly plot this point of outliers to indicate them in the box plot. So if you want to sketch the box plot, you have 31 here and 42 here, somewhere here. So this will be the 2 points corresponding to the outlier, indicated in the box plot. And then, after that, for those numbers that are not outliers, we will construct the box plot according to the 5-number summary. We draw a box. From the lower quartile to the upper quartile. Okay? So this is Q.25. This is Q.75. We draw a box. And then we'll draw a line in between, within the box to indicate the location of the median. So maybe somewhere here. Okay. And besides the box, it is called the box whisker plot, right? So we need to also extend two whiskers to the minimum and maximum, but not the minimum and maximum in the 5-number summary, because this is already the minimum. So we exclude those outliers, and we draw the whisker extended to the minimum and maximum, excluding the outliers. So excluding the outlier, the minimum point that is not outlier is 63, this one. And this is the maximum, also not regarded as outlier. So we extend a line to 63 and extend this to 94. So this is how we sketch the box plot. Okay? Is there any question? So now I still have a little time, so I would like to say a few words about question number 4. Now you will find that question number 4 is quite difficult for you and quite challenging. But I would also like you to attempt to work on it later when you have time, because this is actually a past exam question. So I just want to say a few words so that you know where to start. Now the question states that if you are given a probability density function, the population mean, by definition, it is equal to the integral of x multiplied to the PDF, integrating over the whole data range. This is how we determine the population mean when you are given a probability density function. Now the question says that we can actually use the histogram to estimate the probability density function. So if we replace the f by histogram, then we will obtain an estimated population mean. Now part 1 here is asking us to show that this integral is actually equal to this. Now what should we start with? We know that histogram of x is equal to Vk divided by NH. For x falling within the corresponding class. Okay, so this is the histogram. So we need to substitute this into this integral to do the integration. But the problem here is that this actually will test different value in different class because it depends on the frequency. And therefore, to start with, you can first partition the integral according to the classes. We know that the integration has a feature. We can partition the integration into sub-intervals. So this can be actually written as the sum k from 1 up to capital K integral ak to ak plus 1 s histogram s and then ds, right? The whole integral can be partitioned from the integration from a1 to a2, and then another integral a2 to a3, another integral a3 to a4, and so on, and then we add them up together. Now, after you express this in this form, we know how to write down this histogram S. Because within this range is BK, is the class BK. So that this time this histogram of S will be equal to this. Now, you may start with this one. If you have time when you go home, you may start with this one and then try to show that it is actually given by this. Okay? And if you're still got stuck and you want to have some guide, you can just feel free to drop me an email anytime. Okay? Understand? So, is there any question? Any more questions? Okay. So because I have a meeting, so I'll need to leave. So see you next week.
They're so long.
So super long.
5 minutes each, right?
Yeah.
I haven't done it. I'll do it in 3 days.